We want to group organisms by their common evolutionary descent. So we want to group them by the most closely related groups together. And that's what we use cladistics and phylogenetics for. So those are the systems that help us sort of decipher the evolutionary history of a species so that we can see their connections, how they are genetically related to one another. All the trees that we have here, they actually show exactly the same information, but they can be represented in different orientations. So let's take a closer look at this group here. Here we have, first group we're going to look at is humans and chimps. And we can see that humans and chimps share a recent common ancestor. So that is this number 1. This is the common ancestor of humans and chimps. Now people tend to think that if humans evolved from chimps, how come there are chimps still around? But the truth is we do not evolve from chimps. We share a recent common ancestor with chimpanzees. So it is the same to say, how come if you and your cousins have the same ancestors, how come you still have cousins? Well, you did not evolve from your cousins, rather you and your cousins share the same ancestor, which is your grandparents. Now we can go back into this genealogy, and the way you go more ancestral is going in this direction. The most ancestral part will be over here. This number 3 here will be the ancestor of all of these great apes. So we have the ancestor here, and all the descendants from that ancestor, so all these branches, gibbons branch from there, orangutans branch from there, gorillas, and humans and chimps all branch from this common ancestor. And all these other representations here are exactly the same. They were showing the same relationships. They are simply rotating the angles. But if you see here, it still depicts humans and chimps as the closest, followed by gorillas and orangutans, which is the same thing that we see in all of the cladograms. So these are just different ways to represent the same thing. Just to remember, this part here is where we have the common ancestor. It might be easier to understand phylogenetic trees if we look at something that we're more familiar with, like our family tree. So if we see our family tree, you and your siblings are at the ends of the node, and here at the node you have your parents. So the node represents the ancestor of the branches from that node. Now if we go back, here we have your grandparents. So these are you and your siblings' ancestors, but they're also the ancestors of your cousins. This node here will represent your grandparents. Now note that your cousins here, they do not descend directly from your grandparents. At some point here, you will always have also another ancestor, which are your aunts or uncle, but they are not depicted in the tree. Same thing here, now you have your great-grandparents, and your great-grandparents are the ancestors of your grandparents, but they're also the ancestors of your cousins, your siblings, and you. And over here you have your second cousins. So your second cousins also descended from your great-grandparents. And also take into account that here you will have your grand-aunt or great-grand-uncle, and then here you will have a second uncle, a second-degree uncle or aunt. So they are also ancestors that are along these lines that might not be represented. So you have to imagine that this group here did not instantly evolve from here, but they also have their own genealogy that is not represented for practical purposes. So just like that family tree is the same as our evolutionary trees, just looking farther and farther back into our ancestry. So at some point, us and all other mammals share a common ancestor. So this node here represents an organism that was the last common ancestor of all mammals, the most recent common ancestor of all mammals. And we can keep going back into our genealogy, and we will find an organism that was the last common ancestor, the most recent common ancestor of all vertebrates. So this organism here gave rise to amphibians and also all other vertebrates, including mammals, or other four-legged vertebrates. And so on. If we can keep going back in time, we will find an ancestor that was the ancestor to all vertebrates. And fish are vertebrates, they also descend from that ancestor, and as well as all mammals and tetrapods descend from that ancestor. So keep in mind that the terminals of the tree represent the existing forms. So this is us today, amphibians of today, fish of today, mammals of today. But the nodes here represent the ancestors, so those in the past that are non-existent anymore, but they were the ancestor of those lineages. So this will be the ancestor of these groups, and here the ancestor of these groups. And as we said before, in this path you will also have other older ancestors that are not depicted in the tree, but that doesn't mean that they didn't exist. It's just for practical purposes we don't draw them. So notice that as we go deeper into the tree, that's when we go back into the different ancestors. The order of the groups here at the top doesn't really have any meaning. So it's not that if those on the left are less evolved than those on the right. Actually, there is no such a thing. The ancestors are when you look deeper into the branches of the tree. That's when you see the ancestors. All the organisms listed at the top of the tree, all those in the leaves, so to speak, those are all of the same time. Those are all existing lineages that are present today, that have the same evolutionary history, that have been evolving for the same amount of time. They all trace back to the very first living organism on Earth, and they all are the result of billions of years of evolution. So let's look to how do we reconstruct phylogenies? How do we build these phylogenies? And what we use is the common traits. So we look at which traits are common to each of these groups, and based on that we decide to group them together. So for example, here we have a table showing us the possible traits, so jaws, lungs, amniotic egg, hair, tail, or being bipedal, and whether the organism has it or not. So if they have it, they will have a 1. If they don't, have a 0. Humans and gorillas, as we can see here, they have most of these traits in common, except for just the last one, which is being bipedal. That's unique to humans. But since they share the most number of traits, the first step in building the phylogeny will be to group them together. And that's what we do here. So the first step is we place them together, and we know they share a common ancestor, and that's how they inherited most of those common traits. The next step, we look at the next organism in line, which one shares the most traits with those two. Tigers will be the next in the line, so tigers share the next number of traits, maximum number of traits, with gorillas and humans. So we'll put tigers here, they will be the next in the phylogeny. And following that, lizards will share the next maximum number of traits, so we put lizards over here as being the closest ancestor to tigers and gorillas and humans. And we keep going, and then salamanders and sharks, and finally lampreys. So this grouping happened by comparing the number of traits that these individuals of this species share. The higher the number of traits you have in common, the more closely related you will be. When reconstructing phylogenies, it is very important to keep parsimony into account. And parsimony, what it means is you want to use the path of the least resistance, or the path of the least effort, of the fewer number of steps. If we have here 3 species of birds, 2 of them are red, have red feathers, so this guy's here, and 1 has blue feathers. We can say blue is the ancestral, and then this group evolved the red color on its own, and then this group evolved the red color separately. So that means that we're taking 2 steps for the evolution of the red color. This means we're expecting it to have happened twice, which is less likely than if it only happened once. So if we say blue is the ancestor, and then this group here, the ancestor of these 2 species, already had red feathers, so that these 2 species inherited from the same ancestor. In this case, the evolution of red feathers only had to happen once, right here, and these 2 species inherited from that common ancestor. Let's test our understanding with this exercise. Here we have a phylogeny of all existing reptiles, and the ones in the red circle, which include crocodilians and birds, as well as the dinosaurs, they all have parental care. So they will show behavior in which the adults take care of their babies. Where do you think that parental care evolved? Option A tells us that parental care is ancestral to all reptiles, but it was lost in turtles. So that means parental care evolved over here and it was lost here. So that will require 2 steps. Now the other option, option B, says parental care first appeared in the ancestor of crocodiles and dinosaurs, somewhere around here. Here is the common ancestor of crocodiles, dinosaurs, and birds. So that, if that is the case, that means it would only have to evolve once. And the third option tells us parental care evolved independently on each group. So that would mean it evolved once here in crocodiles, once here in stegosaurs, one in tyrannosaurs, one in velociraptors, and one in birds. So that would be a total of 5 times. Here in these numbers, you can quickly see that the most parsimonious of all these options would be this one, because this is the one that requires the fewer number of steps. In this example, if parental care evolved here in the ancestor of crocodiles, dinosaurs, and birds, and all of those groups inherited from that same ancestor who originally had that trait.